Welcome to Science for Sleep, the place where the biggest mysteries in the universe become the last thing on your mind before you drift off. Tonight, we are going to talk about a planet that has been right there in the night sky for billions of years. A world so strange, so tilted, so completely different from anything else in our solar system, that scientists are only now beginning to realize how little they actually understand about it. A planet that our one and only spacecraft visited for just 6 hours, nearly 40 years ago, and then left behind forever. Tonight, we are going to talk about Uranus. Now, I know what some of you are thinking. Uranus. Really? That planet? The one everyone makes jokes about. The pale blue-green one that sits quietly in the outer solar system, barely visible to the naked eye, rarely mentioned in the same breath as Jupiter or Saturn or Mars. That reaction is exactly the problem. Because while everyone has been looking the other way, Uranus has quietly become one of the most scientifically fascinating objects in the entire solar system. In the last 6 months alone, it has made headlines multiple times. A brand new moon was discovered orbiting it, one so small that even Voyager 2 completely missed it when it flew past. The James Webb Space Telescope mapped its atmosphere in 3 dimensions for the very first time and found something deeply strange happening there. And researchers mining old data from that 1986 flyby made a discovery that overturned nearly 4 decades of scientific consensus about what Uranus actually is on the inside. 4 decades. That is how long we had the wrong picture. And the reason we had the wrong picture is almost unbelievably unfortunate. When Voyager 2 arrived at Uranus on January 24th, 1986, the planet was experiencing a rare solar weather event. A burst of charged particles from the Sun that had compressed its magnetic field into a completely abnormal configuration. The spacecraft saw Uranus in conditions that only occur about 4% of the time. 4%. We sent one spacecraft to Uranus in all of human history, and it arrived during the 4% window when the planet was behaving completely unlike itself. Everything we thought we knew about Uranus for the last 40 years was based on a snapshot taken on one of its worst possible days. Think about what that means. If someone took a single photograph of Earth during the peak of a Category 5 hurricane, and that was the only image of our planet that ever existed, future scientists looking at it might conclude that Earth is a violent, storm-ravaged world where nothing could survive. They would be looking at real data, accurate data, and they would be completely wrong about what Earth is actually like 96% of the time. That is what happened with Uranus. And now, slowly, painstakingly, using new telescopes and reanalyzed old data and fresh eyes on a 40-year-old mystery, scientists are building a completely new picture of this world. And what they are finding is extraordinary. Uranus is not the boring, featureless, unremarkable planet it appeared to be in Voyager 2's famous photographs. It is a dynamic, complex, deeply strange world that may be the most important planet in the solar system for understanding how planets form. Not just here, but everywhere. Around every star, in every galaxy across the observable universe. How important The James Webb Space Telescope recently confirmed that planets like Uranus, ice giants they're called, are almost certainly the most common type of planet in the Milky Way. Not gas giants like Jupiter, not rocky worlds like Earth, ice giants like Uranus. Billions of them, orbiting billions of stars, and we have studied ours so poorly that we are only now beginning to understand what ice giants actually are. So tonight we are going to fix that. We are going to go deep into Uranus, deeper than any video has gone before. We are going to understand why it is tilted almost completely on its side, and what catastrophic event in the early solar system caused that. We're going to go inside it, down through its atmosphere, past the point where the pressure becomes incomprehensible, into the strange interior where water and ammonia and methane exist in a hot, dense, electrically conducting fluid that generates one of the most bizarre magnetic fields ever observed. We are going to meet its 29 moons, every single one of them named after characters from Shakespeare and Alexander Pope, and discover that some of them may be hiding liquid water oceans beneath their icy surfaces. We are going to look at the new discoveries coming in right now, in 2025 and 2026, that are rewriting everything. And we are going to ask the question that planetary scientists are asking themselves more urgently than ever before. When are we going back? Because here is the thing about Uranus that nobody talks about enough. We have sent orbiters to Mercury. We have sent landers to Venus and Mars. We have had spacecraft orbiting Jupiter for years. We spent 13 extraordinary years orbiting Saturn with Cassini. But Uranus, the seventh planet, an ice giant, likely the most representative example of the most common type of planet in the galaxy, has been visited exactly once, by a spacecraft that spent 6 hours there, in 1986. The same year, the Space Shuttle Challenger exploded. The same year, Chernobyl melted down. That is how long ago we last looked at Uranus up close, and we have not gone back since. That is about to change. The National Academy of Sciences, the body that advises NASA on its scientific priorities, ranked a Uranus orbiter mission as the single highest priority for the next NASA flagship mission in its most recent decadal survey. Higher than going back to Mars, higher than exploring the ocean of Enceladus, higher than anything else. The scientists who study the solar system for a living looked at everything we could possibly go and investigate, and they said, Uranus first. Uranus most urgently. Uranus is where the answers are. Tonight, you are going to understand why. Before we go any further, if this kind of content is something you value, if the idea of spending a quiet evening understanding something truly extraordinary about the universe we live in sounds like exactly what you needed tonight, please consider hitting like and subscribing to Science for Sleep. We are a small channel. Every single subscriber genuinely matters to us. It takes 2 seconds, and it means we can keep making this kind of content for you. Thank you. Truly. Now, let us begin at the beginning. Not with Uranus as it is today, but with the moment it was discovered, by a man who did not even realize what he had found. The year is 1781. The city is Bath, England. And a German-born musician who happens to spend his nights building telescopes in his backyard, is about to accidentally become one of the most famous scientists in the world. His name was Friedrich Wilhelm Herschel. He'd come to England from Hanover as a young man of 19, fleeing the French occupation of his homeland with almost nothing in his pockets. He spoke little English. He had no money, no connections, and no prospects, beyond his ability to play music. For years he scraped together a living copying sheet music, teaching piano, performing at concerts, eventually working his way up to becoming the organist at a fashionable chapel in Bath. By his late 30s, he was comfortable, respected, and settled. By all appearances, his story was the modest, quiet story of a talented immigrant musician who had made good in a foreign country. But Herschel had a second life. At night, while Bath slept, he was doing something else entirely. He was building telescopes, not buying them, building them. Grinding his own mirrors by hand from discs of copper, tin, and antimony, casting molten metal in his own basement, and constructing instruments more powerful than anything available at the Greenwich Observatory, the official astronomical institution of England. He was obsessed with seeing farther than anyone had ever seen before. And the reason he built his own telescopes was simple. The ones he could afford to buy were not good enough. By 1781, Herschel was in the middle of his third systematic survey of the night sky. He was cataloguing every star down to magnitude 8, every star slightly too faint to see with the naked eye, checking each one methodically, night after night, building a map of the heavens more complete than anything that existed at the time. It was not glamorous work. It was the astronomical equivalent of counting grains of sand on a beach. But Herschel was relentless. Then, slightly before midnight on March 13th, 1781, something in the eyepiece of his homemade telescope caught his attention. Near the star Zeta Tauri in the constellation Gemini, there was an object that looked slightly wrong. Not dramatically wrong, not shockingly wrong, just subtly, naggingly different from everything around it. Where every other object in the field appeared as a sharp pinpoint of light, this one seemed to have a disk, a small, fuzzy disk rather than a hard point. Herschel noted it in his logbook. His exact words were, "In the quartile near Zeta Tauri, either a nebulous star or perhaps a comet." He was not excited. He was not even particularly curious. Comets were not rare events in the 18th century. They appeared several times a decade and generated brief interest before fading from view. Herschel thought he had found another one. His first published paper about the object was titled simply An Account of a Comet. He moved on and continued his survey. 4 days later, on March 17th, he pointed his telescope at the same patch of sky, and the object had moved. Not by much, but it had shifted position relative to the fixed stars around it, which meant it was not a star at all. It was something much closer to Earth. Herschel confirmed his original suspicion. It was a comet. He reported it to the Astronomer Royal in London, Neville Maskelyne, and thought little more of it. But the astronomers who tried to calculate the orbit of Herschel's comet ran into a problem. Comets move in elongated, highly elliptical paths that take them swooping close to the Sun before flinging them back out into the deep solar system. This object was not doing that. Its orbit was almost perfectly circular, and it was not swooping anywhere near the Sun. It was sitting far out beyond Saturn, moving slowly and steadily in a path that looked nothing like a comet, and everything like something else entirely. About 6 weeks after Herschel's discovery, the Astronomer Royal wrote back to him with one of the most understated sentences in the history of science. Maskelyne wrote, "I don't know what to call it. It is as likely to be a regular planet moving in an orbit nearly circular to the Sun as a comet moving in a very eccentric ellipse." In other words, "Herschel, I think you may have found a planet." The implications of that sentence were staggering. For all of recorded human history, going back to the earliest Babylonian clay tablets, through ancient Egypt, through Greece and Rome and the Islamic Golden Age and the Renaissance, the solar system had contained 6 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn. 6. Always 6. Every civilization that had ever looked at the sky had seen the same 6 worlds. The number 6 was so fundamental to human understanding of the solar system that it was woven into calendars, mythology, religion, architecture, and philosophy across every culture on Earth. And now, in the back garden of a musician in Bath, England, on a perfectly ordinary Tuesday night in March, someone had found a 7th. Herschel became famous overnight. The Royal Society awarded him the Copley Medal, the most prestigious scientific honour in Britain at the time. King George III was delighted, not least because Herschel had shrewdly named the new planet Georgium Sidus, George's star, in the king's honour. Our George rewarded him with an annual pension of £200 and appointed him court astronomer. For the first time in his life, Herschel could afford to give up music entirely and dedicate himself to astronomy full-time. The accidental discovery of a planet had given him the career he had always wanted, but the name Georgium Sidus did not stick. Astronomers outside Britain, particularly in France, had no intention of naming a planet after the British monarch. A German astronomer named Johann Bode proposed an alternative. Uranus, the ancient Greek god of the sky, the primordial deity who preceded even the Titans in Greek mythology, the father of Saturn and grandfather of Jupiter. Bode argued that the name followed the pattern of classical mythology used for all other planets, and that Uranus was the logical choice, since in the mythological family tree, Uranus was the father of Saturn, just as the planet Uranus orbits farther from the Sun than Saturn. It took decades for the name to be universally accepted. Well into the mid-19th century, some astronomers still called it Herschel. But eventually, Uranus won out, and Uranus it has been ever since. There is one more detail about this discovery that deserves a moment. Herschel did not actually discover Uranus in the sense that nobody had ever seen it before. The planet had been observed at least 22 times by different astronomers before 1781, going all the way back to 1690. The English astronomer Royal John Flamsteed had recorded it in his star catalogue in 1690, cataloguing it as a faint star called 34 Tauri. The French astronomer Pierre-Charles Lemonnier observed it 12 separate times between 1750 and 1769 without realizing what he was looking at. 12 times. He had the data. He simply never connected the dots. What Herschel did that none of them had managed was this. He looked at it carefully enough, with a telescope powerful enough, to notice that it had a disk rather than a point. That single observation, the recognition that this object was not a star but something with physical size, was the difference between a curiosity catalogued and forgotten and the discovery of a new world. It was not luck alone that led Herschel to the discovery. It was the quality of his instruments, the obsessiveness of his observation, and the willingness to notice that something was slightly, subtly, naggingly wrong. 6 years after the discovery, Herschel pointed his telescope at Uranus again and found 2 objects orbiting it. He had discovered the first 2 moons of Uranus, worlds that his son John would later name Titania and Oberon, after characters in Shakespeare's A Midsummer Night's Dream. The tradition of naming Uranus's moons after Shakespearean and literary characters had begun. Today, all 29 known moons of Uranus carry those names: Ariel, Umbriel, Miranda, Puck, Caliban, Prospero, Sycorax, an entire celestial system named for the plays and poems of William Shakespeare and Alexander Pope. We will meet them properly later in this story. Herschel spent the rest of his life doing astronomy. He catalogued 2,500 nebulae. He discovered that the sun itself is moving through space rather than sitting still at the center of the solar system. He was the first person to map the shape of the Milky Way, correctly identifying it as a disc-shaped structure. He discovered infrared radiation. He was elected the first president of the Royal Astronomical Society when it was founded in 1820. He died in 1822 at the age of 83, having transformed astronomy more thoroughly than almost anyone before or since. And all of it grew from one quiet night in a Bath garden when a musician looked through his homemade telescope and noticed that one small smudge of light was not quite a star. But the discovery of Uranus only raised more questions than it answered. What exactly was this 7th planet? How large was it really? What was it made of? Why did it seem to behave so differently from Jupiter and Saturn, the other large planets beyond the asteroid belt? For nearly 200 years after Herschel's discovery, the answers to those questions remained frustratingly out of reach. Telescopes improved, observations accumulated, more moons were found. Till the rings were discovered in 1977, just 6 months before Voyager was launched. But the planet itself, its true nature, its interior, its atmosphere, the deep strangeness of it, remained hidden behind that pale blue-green disk until January 24th, 1986, the day humanity finally got close enough to see. On August 20th, 1977, NASA launched a spacecraft called Voyager 2 from Cape Canaveral, Florida. Its original mission was straightforward: fly past Jupiter, then Saturn, study both planets. Oh, and that would be that. A 2-planet mission. Clean, manageable, achievable. But a small group of scientists at NASA's Jet Propulsion Laboratory had noticed something extraordinary about the geometry of the outer solar system in the late 1970s, and they were not willing to let the opportunity pass. Once every 175 years, the outer planets align in a configuration that allows a single spacecraft to visit all 4 of them in sequence: Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity as a slingshot to fling it toward the next. No rocket ever built could carry enough fuel to do this under its own power. But using the planets themselves as gravitational engines, a spacecraft launched at exactly the right moment, on exactly the right trajectory, could make the entire grand tour on a single tank of fuel. That window opened in 1977. The next one would not open until 2152, and NASA had a spacecraft already on the pad. The mission was extended. Voyager 2 would go to all 4 outer planets, if it survived. That was a very large if. The spacecraft was built to last 5 years. The journey to Neptune would take 12. Every component, every circuit, every instrument would have to keep functioning in the cold vacuum of deep space for more than a decade, receiving maintenance from no one, repaired by no one, operating entirely on its own more than 4 billion kilometers from the nearest human hands. It worked. Voyager 2 flew past Jupiter in July 1979. It flew past Saturn in August 1981, and on January 24th, 1986, after traveling 1.8 billion miles from Earth over the course of nearly 9 years, it arrived at Uranus. Closest approach occurred at exactly 1759 UTC. The spacecraft came within 81,500 kilometers of Uranus's cloud tops, closer than any human-made object had ever come to this planet, closer than any human-made object has come since. The encounter that scientists had been waiting 9 years for, that some of them had spent their entire careers preparing for, lasted 5.5 hours. 5.5 hours. That is not a typo. The reason was geometry. Uranus is tilted almost completely on its side, rotating with its poles pointing roughly toward and away from the Sun, rather than up and down like every other planet. Because of this orientation, the moons of Uranus orbit around its equator in a perfect bullseye pattern when viewed from the approaching spacecraft, like rings on an archery target. To fly past Uranus and still have enough trajectory left to reach Neptune 3 years later, Voyager 2 had to thread the needle through the center of that bullseye at enormous speed. There was no way to slow down, no way to linger, no way to take a second look. The spacecraft was moving at 51,000 kilometers per hour. At that speed, the entire Uranian system, the planet, its rings, its moons, was behind Voyager 2 in less than 6 hours. Then it was gone. In those 6 hours, Voyager 2 returned more than 7,000 photographs. It discovered 10 new moons in a single afternoon: Puck, Portia, Juliet, Cressida, Rosalind, Belinda, Desdemona, Cordelia, Ophelia, and Bianca. Every single one of them named for Shakespeare's characters, continuing the literary tradition Herschel had begun 2 centuries earlier. It found 2 new rings, bringing the total known to 11. It measured the length of a Uranian day for the first time, 17 hours and 14 minutes. It detected lightning in Uranus's atmosphere. 140 lightning strikes recorded in a single day, each one releasing around 100 million watts of energy. Every hour of those 6 hours was packed with discovery. But the strangest discovery of all was the magnetic field. Planetary magnetic fields are generated deep inside a planet by the movement of electrically conducting material. In Earth's case, liquid iron in the outer core. The magnetic fields of Jupiter and Saturn are slightly tilted from their rotation axes, just as Earth's is, a few degrees off-center, the way a slightly crooked compass needle still points roughly north. Uranus was completely different. Voyager 2 found that Uranus's magnetic field was tilted 59 degrees from its rotation axis. Not a few degrees. 59 degrees. And it was not even centered on the planet. It was offset from Uranus's center by about 1/3 of the planet's radius, exiting from a point much closer to the surface than the core. It was the most bizarre planetary magnetic field anyone had ever seen. Nothing in planetary science had prepared the scientists at JPL for what Voyager 2 was telling them. A magnetic field this lopsided and off-center would behave in extraordinary ways. Instead of the relatively uniform magnetic bubble that surrounds Earth or Jupiter, Uranus's magnetosphere would tumble and cartwheel through space as the planet rotates, flipping its orientation relative to the solar wind twice every Uranian day. One researcher described it as a badly thrown American football spiraling chaotically through space. No other planet in the solar system has a magnetosphere that behaves remotely like this. Scientists spent years trying to understand why. Then there was the radiation. Voyager 2's instruments measured radiation belts around Uranus, regions of trapped high-energy electrons similar to Earth's Van Allen belts, but at intensities that did not make sense. The radiation levels were far too high. Dramatically, inexplicably too high for a planet whose magnetosphere appeared to be nearly empty of plasma. The charged particle soup that normally fills a planetary magnetosphere and feeds the radiation belts. A nearly empty magnetosphere and extremely powerful radiation belts seem like a physical contradiction. Scientists filed it away as one of Uranus's many mysteries and moved on. That mystery stayed unsolved for 39 years. Then, just a few weeks ago, in February 2026, a team of scientists at the Southwest Research Institute published a paper in Geophysical Research Letters that finally cracked it. They went back to the Voyager 2 data and compared it to something nobody had thought to compare it to in 1986. Space weather events observed near Earth in the decades since the flyby. What they found was a near-perfect match. Voyager 2 had arrived at Uranus during a co-rotating interaction region, a specific type of solar wind disturbance that occurs when fast-moving streams of solar wind slam into slower ones, creating a compressed region of intensified energy. On Earth, these events are well studied. They dramatically supercharge the Van Allen belts, temporarily flooding them with extra high-energy electrons, exactly what Voyager 2 had measured at Uranus. The spacecraft had not arrived at a normal Uranus. It had arrived during a cosmic perfect storm, the empty magnetosphere the feature that had defined scientific understanding of Uranus for 4 decades, was empty, not because Uranus's magnetosphere is naturally empty, but because the solar wind event had swept the plasma out, compressing the magnetic bubble and leaving it temporarily hollow. Dr. Jamie Jasinski, the lead author of the study, said it plainly. If Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere at Uranus. The spacecraft saw Uranus in conditions that only occur about 4% of the time. This is a humbling result. It means that the planet's scientists have been studying, debating, and building theories about for nearly 40 years was not the real Uranus. It was Uranus having an unusually bad day. The real Uranus, the normal day-to-day Uranus that exists 96% of the time, has never been directly observed by any spacecraft. We have one flyby, taken on one of its worst days, and that has been our entire direct knowledge of this planet's magnetic environment for 4 decades. The implications go further. If the magnetosphere was behaving abnormally during the flyby, then some of the conclusions drawn from it may also be wrong. One of them, in particular, stands out. Voyager 2's data had suggested that Uranus's major moons were geologically inactive, quiet, dead, frozen worlds, with nothing interesting happening beneath their surfaces. But the new research shows that this conclusion was based on the abnormal magnetospheric conditions. With a normal magnetosphere, the picture looks different. The moons, particularly the 2 largest outer ones, Titania and Oberon, may actually orbit outside Uranus's magnetosphere most of the time, which means something extraordinary. It may be possible for a future spacecraft to detect subsurface oceans on those moons without the magnetosphere interfering with the measurements. Moons that were written off as dead may actually be alive. We just caught them on the wrong day. There was one more discovery from that 1986 flyby that deserves its own moment, because it remains one of the most visually stunning things Voyager 2 found anywhere in the solar system. Its name is Miranda. Miranda is the smallest of Uranus's 5 large moons, only 471 kilometers in diameter, barely larger than some asteroids. By every expectation, it should have been the least interesting target of the flyby. A small, cold, ancient, crater-covered ball of ice sitting in the outer solar system. Nothing to write home about. Voyager 2 passed within 26,000 kilometers of it, its closest encounter with any body in the Uranian system, and what its cameras revealed caused scientists at JPL to stop what they were doing and stare. Miranda is a geological nightmare. Its surface is covered in enormous fault scarps, cliffs of ice rising up to 20 kilometers high, the tallest known cliffs in the solar system. For comparison, Mount Everest stands 8.8 kilometers above sea level. Miranda has ice cliffs more than twice that height. Alongside the cliffs are parallel grooves and ridges called coronae, strange banded features unlike anything seen on any other world, mixed with ancient cratered terrain. The whole surface looks like it was shattered into pieces and then reassembled by something that did not quite know what it was doing. One researcher at the time described it as the most chaotic terrain in the solar system. The leading explanation is that Miranda was hit by something catastrophic early in the solar system's history. Hit so hard that it shattered completely, broke apart into fragments. And then, slowly, over millions of years, the fragments were pulled back together by gravity. But they did not reassemble neatly. The different pieces of the original moon, each one with its own internal structure, its own geology, its own layering, came back together in a jumble, all fusing into a single body that carries the geological fingerprints of a violent dismemberment and a messy reconstruction. Miranda is, in a very literal sense, a moon that died and came back to life. And the only close-up images we have of it were taken during 6 frantic hours in January 1986. 5.5 hours at Uranus, 7,000 photographs, 10 new moons, 2 new rings, a day length finally measured, lightning detected, a magnetic field unlike anything in the solar system, a radiation mystery that would take 39 years to solve, and Miranda, the Frankenstein moon, staring back at the cameras with its impossible cliffs and its shattered, reassembled face. And then Voyager 2 kept going. 2 weeks after closest approach, engineers fired its thrusters for the largest course correction in the spacecraft's history, a burn lasting 2.5 hours, to aim it precisely at Neptune. 3 years later, in August 1989, it flew past the final planet on its itinerary. And then it kept going still. Out past Neptune, out past the Kuiper Belt, out past the heliopause where the sun's influence finally fades, and into the interstellar medium where it is traveling right now at 55,000 kilometers per hour, carrying the golden record with its greetings from Earth, getting a little farther every second from the blue-green planet that sent it. Uranus watched it go. And then it was alone again, the way it has always been, rolling silently through the outer solar system, tilted on its side, its magnetic field cartwheeling through space, its 29 moons circling in their literary parade, waiting. 40 years it has been waiting. And what scientists have learned about it in those 40 years, mostly from telescopes on Earth and in orbit, mostly from reanalyzing those 7,000 photographs over and over with new tools and new techniques, has only made the waiting feel more urgent. Because the more closely they look, the stranger Uranus becomes. And the stranger it becomes, the more important it is that we go back. But before we talk about what comes next, we need to understand what Uranus actually is. Not its history, not its discovery, not the 6 frantic hours of Voyager 2's visit. What it actually is, physically, from the top of its atmosphere all the way down to whatever lies at its center. Because that story turns out to be one of the most genuinely mysterious things in planetary science. To understand what Uranus actually is, you have to let go of every intuition you have about what a planet looks like on the inside. When most people picture a planet, they picture something like Earth, a solid surface you could theoretically stand on, with layers below it getting progressively hotter and denser until you reach a molten core. Uranus does not work that way. There is no surface on Uranus, no ground, no place where the atmosphere ends and something solid begins. If you descended into Uranus, you would not land on anything. You would just sink deeper and deeper as the gas around you became denser and hotter and more pressurized, until the distinction between gas and liquid ceased to mean anything at all. Let us take that descent together, starting from the top. The first thing you would encounter is the atmosphere, the pale blue-green layer that gives Uranus its distinctive color and the only part of the planet we have ever directly observed. The color comes from methane. About 2.3% of Uranus's outer atmosphere is methane gas, and methane has a very specific optical property. It absorbs red and orange wavelengths of light and reflects blue and green ones. So, when sunlight hits Uranus's atmosphere, the red end of the spectrum is swallowed up, and what bounces back to your eyes is that characteristic pale aquamarine. If you removed all the methane from Uranus's atmosphere, the planet would appear nearly colorless. That single molecule, one carbon atom bonded to 4 hydrogen atoms, is responsible for one of the most recognizable colors in the solar system. Below the methane layer, the atmosphere transitions through a series of distinct cloud decks. Methane ice clouds sit at the top. Below them, clouds of hydrogen sulfide. Lower still, clouds of ammonia and ammonium hydrosulfide. And deeper than those, in the troposphere, where pressures reach several times Earth's atmospheric pressure and temperatures climb despite the depth. Water clouds, enormous structures of water, droplets and ice suspended in a hydrogen and helium atmosphere, hundreds of kilometers below the top of the cloud deck. You could not see these clouds from outside the planet. They are buried under so many layers that they are essentially invisible to telescopes. We know they are probably there because the physics and chemistry of the atmosphere demands it. But we have never directly observed them. As you sink deeper, the temperature and pressure increase relentlessly. The gas becomes denser. The boundary between gas and liquid begins to blur. And eventually, somewhere between the outer atmosphere and the deep interior, you would cross into a region that planetary scientists call the ice mantle. Though the word ice here is deeply misleading and worth spending a moment on. When scientists call Uranus an ice giant, they do not mean that the interior is frozen. They mean something quite different. In the extreme pressures found deep inside Uranus, pressures millions of times higher than Earth's atmospheric pressure, water, ammonia and methane do not behave the way they do at the surface of the Earth. They are not solid ice. They are not conventional liquids. They are not gas. They exist in a state that has no good everyday equivalent. A hot, dense, electrically conducting fluid where molecules are constantly breaking apart and reforming, where hydrogen atoms detach from their oxygen partners and drift freely through the structure, where the material conducts electricity almost as well as a metal. Scientists call it superionic water or ionic fluid, and it is one of the most exotic states of matter in the known universe. You could not touch it, bottle it, or describe it with any word from ordinary experience. It simply does not have an equivalent in daily life. This ionic fluid mantle is believed to make up roughly 60% of Uranus's total volume. It is the defining feature of what makes an ice giant different from a gas giant like Jupiter or Saturn. Jupiter and Saturn are dominated by hydrogen, enormous quantities of it, compressed at their cores into metallic hydrogen that generates their powerful magnetic fields. Uranus has far less hydrogen and far more of these heavier, more complex molecules, water, ammonia, methane, sitting in that strange ionic fluid state. The result is a planet that looks superficially similar to Jupiter and Saturn from the outside, but is physically a completely different class of object on the inside. At the center of all of this sits the core, and here is where things get even more uncertain. For decades, the standard model assumed Uranus had a small, dense, rocky core, perhaps 1 to 3.5 times the mass of Earth, surrounded by the ionic fluid mantle and then the outer atmosphere. It was a tidy, layered model: rocky core, icy mantle, gaseous atmosphere. 3 distinct regions, each one sitting cleanly inside the next like nested dolls. But in December 2025, a team of researchers at the University of Zurich published a paper that challenged this model at its foundation. Led by PhD student Luca Morf and Professor Ravit Heled, they developed a new simulation technique that did not assume anything about the composition of Uranus's interior in advance. Instead of starting with a model and testing whether the data fit it, they started with the data, the gravitational field measurements, the density profile, and the orbital characteristics, and worked backward to see what kinds of interiors could possibly produce those observations. What they found was deeply unsettling for anyone who thought the interior of Uranus was well understood. The answer was not one interior, it was many. The data, as it currently stands, is consistent with Uranus being ice-rich on the inside, the traditional model, but it is equally consistent with Uranus being rock-rich. The rocky core that scientists assumed was a minor feature at the center might actually dominate the entire interior. Uranus might not be an ice giant at all. It might be a rock giant, or something in between, or something entirely different from either category. As Morf stated plainly in the paper, the ice giant classification is oversimplified, as Uranus and Neptune are still poorly understood. Current data are insufficient to distinguish between the possibilities. We need dedicated missions to reveal the true nature of what lies beneath that blue atmosphere. This is a remarkable admission about a planet in our own solar system. We genuinely do not know what is inside Uranus. We have been calling it an ice giant for decades, putting it in textbooks, teaching it to students, and it turns out the classification may be wrong. The interior could be fundamentally different from everything we assumed. The only way to find out is to go there, to send an orbiter with instruments sensitive enough to map the gravitational field with precision, to probe the magnetic field in detail, to eventually drop a probe into the atmosphere that can sample it directly. We do not have that data yet. Everything we know about the interior of Uranus is a model built on incomplete observations from one rushed flyby and 40 years of telescope work from 2.7 billion kilometers away. Now let us talk about something happening right now. in 2025 and 2026 that is giving scientists their best look yet at the outer layers of this mysterious planet, without sending a single spacecraft to Uranus. On January 19th, 2025, the James Webb Space Telescope pointed its instruments at Uranus and watched it for 15 consecutive hours, nearly one complete Uranian rotation. The telescope used its near-infrared spectrograph, one of the most sensitive instruments ever built for space observation, to detect the faint glow of molecules high above the planet's cloud tops, in a region called the ionosphere, the upper boundary of the atmosphere, where it becomes ionized and begins to interact directly with the planet's magnetic field. What Webb produced from those 15 hours was the first ever three-dimensional map of Uranus's upper atmosphere. Not a flat image, not a single measurement. A full three-dimensional portrait of how temperature and ion density vary with height across the entire planet, from the cloud tops all the way up to 5,000 kilometers above them. Lead researcher Paola Tiranti of Northumbria University described it simply: "This is the first time we have been able to see Uranus's upper atmosphere in 3 dimensions. With Webb's sensitivity, we can trace how energy moves upward through the planet's atmosphere and even see the influence of its lopsided magnetic field." 2 things came out of this observation that deserve particular attention. The first was the auroras. Webb detected 2 bright auroral bands near Uranus's magnetic poles, the most detailed view anyone has ever obtained of where Uranian auroras actually form and how they behave. On Earth, auroras form in roughly circular rings around the magnetic poles, because Earth's magnetic field is relatively aligned with its rotation axis. On Uranus, where the magnetic field is tilted 59 degrees and offset from the center, the auroras do not form in simple rings. They sweep and tumble across the upper atmosphere in complex, shifting patterns that change twice every Uranian day, as the magnetic field rotates through different orientations relative to the solar wind. Webb finally showed, in direct observation rather than theoretical prediction, exactly how this works. The auroras of Uranus are unlike anything in the solar system, and they are spectacular. The second finding from the Webb observation was more troubling. The data confirmed and extended a trend that ground-based telescopes had been tracking since the early 1990s. Uranus's upper atmosphere is cooling down, steadily, measurably, over more than 3 decades. Webb measured an average ionospheric temperature of around 426 Kelvin, approximately 150 degrees Celsius, which is lower than temperatures recorded by any previous instrument at any previous time. The cooling trend that began sometime in the late 1980s or early 1990s is still ongoing. The upper atmosphere of Uranus is getting colder year by year, and nobody knows exactly why. This connects to one of the deepest mysteries about Uranus, one that has puzzled planetary scientists since Voyager 2 first measured it in 1986. Uranus emits almost no internal heat. Every other planet in the outer solar system radiates more energy than it receives from the Sun. They are still slowly cooling from the heat of their formation, and that leftover primordial warmth leaks out into space. Jupiter emits about 1.7 times more energy than it receives from the Sun. Saturn emits about 1.8 times more. Neptune, Uranus's near twin in size and composition, emits about 2.6 times more energy than it receives. Uranus emits essentially the same amount of energy it receives, not more, the same, as if it has no internal heat at all. This is bizarre. Uranus formed from the same processes as the other outer planets, in the same solar system, at roughly the same time. It should have a hot interior left over from its formation, and slowly radiating heat into space over billions of years. But it is not. The heat has gone somewhere, or been blocked somehow. Or perhaps the giant impact that knocked Uranus onto its side also blasted away most of its primordial heat in a single catastrophic event 4.5 billion years ago. The leading hypothesis is that some kind of compositional barrier exists inside Uranus, a layer where convection stops and heat simply cannot move upward, trapping it in the deep interior and preventing it from reaching the surface. But no one has confirmed this. No instrument has ever reached deep enough inside Uranus to test the hypothesis. And now Webb is telling us the upper atmosphere is actively cooling. If the interior is sealed off and the upper atmosphere is losing heat to space, what does that mean for the long-term energy balance of the planet? Is Uranus slowly, over geological timescales, becoming colder? Is something changing in its interior that is altering how heat moves through its layers? These are not rhetorical questions. They are open scientific problems that nobody currently knows how to answer with the data available. What all of this tells us, the uncertain interior, the bizarre magnetic field, the missing heat, the cooling atmosphere, the JWST auroras, is that Uranus is not the simple, quiet, featureless planet it appeared to be in 1986. It is a dynamic, complex, a deeply mysterious world that is actively doing things we do not understand, following rules we have not yet figured out, hiding secrets in its interior that our instruments have never been able to reach. The pale blue-green disk that rolls quietly through the outer solar system is not quiet at all. It is churning. Its magnetic field is cartwheeling. Its atmosphere is cooling. Its auroras are sweeping complex patterns across its upper layers. Its interior might be rock, might be ice, might be something in between that our current models cannot even properly describe. And somewhere beneath all of that, at the very center, sits whatever is left of the original rocky material that came together 4.5 billion years ago when the solar system was young. A core that has never been observed, never been sampled, and whose true nature remains one of the most compelling open questions in planetary science. We've looked at the planet from the outside. We have spent 6 frantic hours flying past it once. We have watched it through the most powerful telescope ever built. And still, Uranus keeps its deepest secrets. Which is exactly why, when planetary scientists were asked to name their single highest priority for the next generation of solar system exploration, they did not hesitate. They said, "Go to Uranus." and find out what it actually is. Every planet in the solar system has moons. Mars has 2 small captured asteroids, barely worth the name. Venus and Mercury have none. Earth has one, large, geologically active, and almost certainly responsible for the conditions that allowed life to take hold on our world. Jupiter has 95. Saturn has 146. But no planet in the solar system has moons quite like Uranus. Not because of their number, although 29 is respectable. Not because of their size, although the largest of them rival the smaller planets. But because of their names. Every single moon of Uranus is named after a character from English literature, not Greek mythology. Not Roman mythology, not the names of gods or titans or sea monsters that dominate the naming conventions everywhere else in the solar system. English literature, specifically the plays of William Shakespeare and the poems of Alexander Pope. When you look up at Uranus and think about the worlds orbiting it, you are looking at a system populated by Titania and Oberon from A Midsummer Night's Dream, by Ariel and Caliban and Prospero and Miranda, and Sycorax and Setebos from The Tempest, by Puck from the same, by Portia and Juliet and Cressida and Desdemona and Rosalind, from the tragedies and comedies, by Umbriel and Belinda from Pope's The Rape of the Lock. Astronomers have nicknamed them the literary moons. And somewhere out there, in the cold dark of the outer solar system, Hamlet circles an ice giant planet on an orbit that takes 3,000 days to complete. The tradition began, as we have seen, with William Herschel, who named the first 2 moons he discovered in 1787, Titania and Oberon, the Queen and King of the fairies in A Midsummer Night's Dream. His son John continued the tradition, naming 4 more moons, Ariel, Umbriel, and later Titania's companions from the Shakespeare canon. And so it went, discovery after discovery, century after century, every new moon of Uranus receiving a literary name rather than a divine one. When Voyager 2 found 10 new moons in a single afternoon in 1986, the naming committee at the International Astronomical Union had to read through the complete works of Shakespeare at speed to find enough suitable characters. They found them. They always find them. Shakespeare wrote over 1,200 named characters across 37 plays. Uranus currently has 29 moons. There is no shortage of names. The newest moon, discovered not by Voyager 2 or by ground-based telescopes, but by the James Webb Space Telescope in images taken on February 2, 2025, is currently designated S/2025U1. It sits between the orbits of 2 existing moons, Ophelia and Bianca, in the inner ring region of the Uranian system. It is tiny, only about 8 to 10 kilometers in diameter, roughly the size of a small city. At that size, it is by far the smallest moon of Uranus ever found. To put that in perspective, the moon we are looking at when we gaze up at the night sky from Earth is 3,474 kilometers across. S/2025. U1 is smaller than the distance between 2 neighboring exits on a motorway. What makes this discovery remarkable is not just its size, but its invisibility. Voyager 2 flew within 81,500 kilometers of Uranus and spent 5.5 frantic hours photographing everything it could see. It found 10 moons in that time, but S/2025 U1, sitting right there in the inner ring system, or orbiting in plain sight, was simply too small and too faint for Voyager's instruments to detect. The Hubble Space Telescope, which has been observing Uranus repeatedly for decades, also missed it entirely. It took the James Webb Space Telescope, the most sensitive observatory ever placed in space, orbiting 1.5 million kilometers from Earth and shielded from the sun by a tennis court-sized sunshield, to finally see it. 10 long-exposure images, each one 40 minutes long, stacked and processed over months of careful analysis before the tiny moving dot revealed itself. Dr. Mariam El-Mutamid of the Southwest Research Institute, who led the team that found it, captured the moment perfectly when she said, "With so many of Uranus's moons named for Shakespearean characters, our team is getting a lot of culture trying to figure out what to name our new discovery. Now, the moon will eventually receive its permanent Shakespearean name from the International Astronomical Union. Until then, it remains S/2025 U1, a dry label for what is actually a genuinely thrilling discovery. A world so small it was invisible to every instrument pointed at Uranus for 40 years, finally seen by the sharpest eyes humanity has ever built. The discovery also raises an obvious question. If Webb found a moon that Voyager, Hubble, and every ground-based telescope missed, how many more are out there? Planetary scientist Matthew Tiscarino of the SETI Institute, who was part of the discovery team, said it directly. No other planet has such a quantity of small inner moons as Uranus, and it is possible that more remain to be discovered. The number 29 may well increase in the coming years as Webb continues its observations and as other instruments push the sensitivity limits further. The literary canon of Shakespeare is deep enough to handle whatever comes. But it is not the tiny new moon that are scientists most excited about the Uranian system. It is 5 much larger worlds that have been known for decades, but studied, like Uranus itself, almost entirely from one rushed flyby and 40 years of distant observation. These are the 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. And recent research is suggesting that some of them may be among the most scientifically significant objects in the entire solar system. We have already met Miranda and her impossible cliffs in Act 3. But Miranda is just the beginning. Let us look at the others. Ariel is perhaps the most intriguing of the 5 major moons right now, and it is the one that planetary scientists are watching most closely. It is 1,157 kilometers in diameter, slightly smaller than Miranda, and its surface is unlike anything else in the Uranian system. Where the other major moons are heavily cratered and ancient-looking, Ariel has the brightest and almost certainly the youngest surface of all 5. Its large craters have been wiped away, obliterated by something more recent. What remains instead is a surface crisscrossed by enormous flat-floored valleys called grabens, where the crust has stretched and split apart, and something has welled up from below to resurface the terrain. That resurfacing agent is believed to be water, or more precisely, a mixture of water and ammonia that flows as a slurry at temperatures far below the freezing point of pure water, acting as a kind of antifreeze lava. The implication of a resurfaced, geologically young surface is significant. Something inside Ariel was warm enough, recently enough, to melt its interior and push material up through its crust. On a tiny moon sitting billions of kilometers from the Sun, with almost no sunlight to drive any kind of surface activity, the only plausible source of that heat is tidal friction, the gravitational kneading produced by Uranus's enormous mass flexing and compressing the moon as it orbits. And if Ariel's interior has been warm enough to melt, if there has been liquid water flowing beneath its surface, then there is a genuine possibility that Ariel harbors, or has recently harbored, a subsurface ocean. Planetary scientist Richard Cartwright of the SETI Institute, who studies the Uranian moons intensively, has called Ariel the most interesting moon and the best target for improving our understanding of ocean worlds in the outer solar system. That is a significant statement. Europa gets all the attention for its hidden ocean. Enceladus gets its plumes photographed by spacecraft and celebrated in press releases. But Ariel, small, quiet, named for a spirit in Shakespeare's Tempest, may be sitting out there with its own subsurface ocean, waiting for someone to come and look properly. An umbriel is the darkest of the 5 major moons, its surface coated in material so dark that it reflects less light than almost anywhere else in the Uranian system. The contrast between Ariel and Umbriel, which orbit at similar distances from Uranus and should in theory have similar compositions, is one of the outstanding mysteries of the system. Why is one so bright and one so dark? The leading explanation involves a difference in the amount of carbon-rich material on their surfaces, possibly delivered by different rates of impact from outer solar system objects over billions of years. But nobody has confirmed this. Umbriel has also shown hints of a bright ring of material on one of its crater floors, possibly ammonia-rich ice exposed by a relatively recent impact. Again, the word recent is doing a lot of work in a system where we have only one observation taken once. In 1986, Titania is the largest moon of Uranus, 1,578 kilometers across, larger than Pluto's moon Charon, large enough to have been pulled by its own gravity into a roughly spherical shape. Like Ariel, Titania shows evidence of geological activity. Enormous canyons up to 1,600 kilometers long and 75 kilometers wide, cutting across its surface. Evidence that its interior expanded at some point in the past, stretching the crust apart and creating rifts that dwarf anything on Earth. The walls of these canyons drop kilometers into shadow. A spacecraft orbiting Titania and looking down into those rifts would be seeing geology on a scale that has no equivalent anywhere in the inner solar system. Oberon is the outermost of the 5 major moons and the second largest, 1,523 kilometers across. Its surface is old and heavily cratered, one of the most heavily cratered surfaces in the Uranian system, suggesting that, unlike Ariel and Titania, it has not been resurfaced by recent geological activity. But Oberon has a mystery of its own. Voyager 2 photographed a mountain rising from its surface to a height of at least 6 kilometers, taller than Mont Blanc, the highest peak in the Alps, sitting isolated on the limb of the Moon with no obvious geological context. Where did it come from? Is it the central peak of an enormous impact crater? Is it the remnant of an ancient volcanic structure? Nobody knows. It has been sitting there since 1986 in the one photograph we have of it, and no instrument has looked at it closely enough to answer the question since. What recent research has done is take the new understanding of Uranus's magnetosphere, the corrected picture that emerged from the reanalysis of Voyager 2's data, and apply it to the major moons. The results are striking. Under normal magnetospheric conditions, which exist 96% of the time, the four outer major moons, Ariel, and Umbriel, Titania, and Oberon, actually spend most of their orbits outside Uranus's magnetosphere entirely. This means they are directly exposed to the solar wind for a significant fraction of every orbit, which has implications for the chemistry of their surfaces and the detectability of any subsurface oceans they might possess. On Europa and Enceladus, the moons that generate the most excitement about extraterrestrial life, and detecting subsurface oceans is complicated by the fact that they sit deep inside their host planet's magnetosphere, which interferes with certain types of electromagnetic measurements. The Uranian major moons, sitting partly outside the magnetosphere, offer a cleaner detection environment. If a future spacecraft could measure the electromagnetic signatures of salty subsurface oceans on Ariel or Titania, it might be able to do so with less interference than anywhere else in the outer solar system. The very feature of the Uranian system that seemed like a complication, the weird off-center magnetic field, might actually turn out to be an advantage for ocean detection. Then there are the irregular moons. Beyond the 5 major moons and the swarm of small inner moons circling close to the rings, Uranus has a collection of outer moons following strange, highly inclined, often retrograde orbits that suggest they were captured from elsewhere rather than formed alongside the planet. Caliban, Sycorax, Prospero, Setebos, Stephano, all names from The Tempest, the Shakespeare play that dominates the outer Uranian system's naming conventions. These moons are dark, small, and almost certainly captured Kuiper Belt objects. Icy bodies from the outer edge of the solar system that wandered too close to Uranus and were trapped by its gravity billions of years ago. Studying them closely could tell us about the composition of the early outer solar system and the migration history of the planets during the chaotic early period when gravitational interactions were reshuffling everything. 29 moons, all named for characters from literature. Each one a world with its own surface, its own geological history, its own unresolved mysteries. The smallest barely larger than a city. The largest bigger than Pluto's moon. Some of them possibly hiding liquid water oceans beneath ice that has never been sampled. All of them studied from one flyby 40 years ago when the spacecraft spent 5.5 hours threading the needle through their orbits before disappearing into the darkness toward Neptune. And somewhere in that system, orbiting quietly, is a tiny unnamed moon, S/2025U1, waiting for its Shakespearean name. The team that found it is reading the plays. The IAU committee will deliberate. And eventually, one more character from English literature will join the parade of worlds circling the sideways planet in the outer solar system. One more name from the page of a 400-year-old play, given to a real world billions of kilometers from the desk where Shakespeare wrote it. The universe has stranger poetry in it than any poet has ever managed to write about it. And Uranus, with its tilted axis and its cartwheeling magnetic field and its 29 literary moons, I might be the most poetic planet of all. There is one question about Uranus that every person asks the moment they learn about it. Before the missing heat, before the bizarre magnetic field, before the 29 literary moons. The first question is always the same. Why is it sideways? Uranus has an axial tilt of 97.77 degrees. Every other planet in the solar system rotates with its axis pointing more or less upward, tilted a little, the way a spinning top wobbles slightly off vertical, but fundamentally upright relative to the plane of its orbit. Earth is tilted 23.5 degrees, Mars 25 degrees, Saturn 26. Even Venus, which rotates backward, is only tilted 177 degrees, still recognizably in the same family of tilts as everyone else. Uranus is at 97.77 degrees. Its rotational axis lies almost perfectly in the plane of its orbit. It does not spin upright like a top. It rolls through space like a bowling ball on its side. Its poles pointing roughly toward and away from the sun rather than up and down. This tilt is so extreme and so unlike every other planet that there is almost no natural explanation for it. A planet forming from the same rotating disk of gas and dust as everything else should end up spinning in roughly the same direction, with a modest tilt at most. The solar system's standard formation process does not produce anything like 97.77 degrees. Something had to have happened to Uranus after it formed. Something violent. Something that hit it hard enough to knock a planet the size of 14 Earths almost completely onto its side and leave it there permanently. The leading explanation is called the giant impact hypothesis. Early in the solar system's history, roughly 4 billion years ago, when the planets were young and the outer solar system was still a chaotic, collision-filled place, a massive object, a protoplanet, an icy body with a mass somewhere between 1 and 3 times the mass of Earth, hit Uranus at an oblique angle. Not a head-on collision. A glancing blow. A grazing impact that did not punch straight through the planet, but instead delivered an enormous sideways kick. A colossal transfer of angular momentum that spun Uranus slowly, agonizingly over onto its side. Computer simulations support this. Smoothed particle hydrodynamics models. Simulations that treat planetary material as millions of individual particles, each following the laws of physics, show that a protoplanet of the right size, hitting at the right angle, at the right speed, can tilt Uranus from whatever its original orientation was to its current 97.77 degrees in a single event. The impact would have lasted perhaps an hour or two. In the space of an afternoon in geological time, the planet's entire rotational axis shifted by close to 100 degrees, and then it stayed there. Nothing in the subsequent 4 billion years of Uranus's history has been powerful enough to push it back upright. But here is the problem with the single giant impact theory. If one enormous collision knocked Uranus sideways, the moons should have been disrupted. The 5 major moons, Titania, Oberon, Ariel, Umbriel, Miranda, all orbit Uranus in the plane of its equator, moving in the same direction as the planet rotates. If a single massive impact had suddenly tipped Uranus onto its side, those moons would have kept their original orbits. They would have continued moving in the plane of the old equator, not the new one. They would not have migrated neatly into the plane of the new tilted equator. They would orbit in the wrong direction, in the wrong plane, a permanent record of the disruption. They do not. All 5 major moons orbit exactly in the plane of Uranus's tilted equator, moving in the right direction. This is the problem that Alessandro Morbidelli of the Observatoire de la Côte d'Azur in Nice, France, and his team attacked with their simulations. What they found was that a single giant impact cannot reproduce both the tilt and the correct orbital directions of the moons simultaneously. If you tilt Uranus all in one shot, the moons end up retrograde, orbiting in the wrong direction. The only way to produce Uranus as it actually exists, with its correct tilt and its correctly orbiting moons, is to hit it at least twice. 2 impacts, not 1. Both of them occurring very early, when Uranus was still surrounded by the protoplanetary disk from which its moons would eventually form. The first impact partially tilted the planet. The second impact finished the job. Between the impacts, the disk of material surrounding Uranus would have migrated, adjusted, reformed around the new equatorial plane. When the moons eventually coalesced from that disk, they inherited the tilted equator of a planet that had been knocked sideways in 2 stages rather than 1. The moons are prograde, orbiting in the right direction, because they formed after the tilting was complete, from material that had already settled into the new equatorial plane. Morbidelli was direct about what this means for planetary science more broadly. The standard theory of planet formation assumes that the giant planets, Uranus, Neptune, Jupiter, Saturn, grew by sweeping up only small objects from the protoplanetary disk. No giant collisions, no catastrophic impacts. A gentle, orderly process of accumulation. But if Uranus was hit at least twice by objects each with a mass comparable to Earth, then giant collisions were not rare exceptions in the outer solar system. They were common events. The standard theory, he said, has to be revised. The solar system's youth was far more violent than the textbooks have been saying. But there is a third theory, even stranger than the 2 impact scenario, and it deserves a moment. In 2022, a research team proposed that Uranus was not knocked sideways by any impact at all. Instead, they suggested it was pulled sideways, very slowly, over millions of years, by a moon. The idea works like this. Early in its history, Uranus may have had a large moon, larger than any of its current moons, orbiting at just the right distance to be in gravitational resonance with the planet's spin. Resonances are orbital configurations where two bodies influence each other in regular, rhythmic ways, like a child being pushed on a swing at exactly the right moment, each push adding a little more to the swing's amplitude. In this scenario, the resonance between Uranus and its large moon gradually transferred angular momentum from the planet's spin to the moon's orbit, slowly tilting Uranus's rotational axis degree by degree over millions of years. And then, once the moon had pushed the tilt past a certain critical angle, it spiraled inward and crashed into Uranus, locking the tilt at its current value and destroying itself in the process. The culprit that tipped Uranus sideways then vanished into the planet it had spent millions of years tilting. This theory neatly explains something the impact hypotheses struggle with. If Uranus was violently hit one or twice, those impacts should have injected enormous amounts of energy into the planet's interior, energy that should still be radiating out as heat today, the way Neptune's interior heat still leaks into space. But Uranus has essentially no excess internal heat. The giant impact hypothesis would need to explain why a catastrophic collision left no thermal signature. The slow resonance theory avoids this entirely. No violent energy injection, no missing heat. The planet was tipped gradually and gently, and its thermal state was not dramatically disturbed. The weakness of the resonance theory is that it requires a large primordial moon that no longer exists and left no other trace in the system. There is no direct evidence for this moon. It is inferred entirely from what the mathematical models require, which is not unusual in planetary science. Neptune itself was inferred from mathematics before it was ever seen. But it does leave the theory on less firm observational ground than the impact scenarios. So 3 competing theories sit on the table. 1 giant impact, 2 smaller impacts, a lost moon dragging the planet sideways over millions of years, each one supported by mathematical models, each one with strengths and weaknesses, none of them proven. And the only way to prove any of them is to study Uranus from close range, to measure its interior structure, its gravitational field, its composition with enough precision to fingerprint which scenario actually produced the planet as it exists today. That requires a spacecraft in orbit around Uranus, which we do not have. What we do have is a very clear picture of the consequences of that ancient tilt, whatever caused it. And the consequences are extraordinary. Uranus takes 84 Earth years to complete one orbit around the Sun. With its rotational axis tilted 97.77 degrees, each of its poles spends 42 years pointing roughly toward the Sun and 42 years pointing roughly away from it. On Earth, the 23.5-degree tilt produces seasons that last 3 months and shift temperatures by a few tens of degrees. On Uranus, the seasons last 21 years each, and the contrast between a polar summer and a polar winter is not a temperature swing of a few dozen degrees. It is the difference between 42 years of continuous sunlight and 42 years of continuous darkness. Think about what that means for the atmosphere. During a Uranian summer, one pole receives more total sunlight than the equator. During winter, it receives none at all. Not a single photon from the sun for more than 4 decades. The atmosphere must respond to these swings, shifting its circulation patterns radically over timescales of decades. Weather systems that form in polar summer must eventually die in polar winter. The jet streams and storm bands that characterize the atmospheres of Jupiter and Saturn, which experience normal seasons, would be completely disrupted on Uranus by this 42-year cycle. And yet, when Voyager 2 arrived in 1986, during the southern hemisphere summer, when the South Pole was pointing more or less toward the sun, the atmosphere looked almost completely featureless, bland, smooth, barely a cloud visible. This was deeply puzzling. A planet experiencing an extreme season should have a dynamic, storm-filled atmosphere responding to the uneven heating. Instead, Uranus looked like a pale blue-green billiard ball, placid and featureless. Recent observations from Hubble and JWST have started to complicate that picture. As Uranus moved toward its northern spring equinox in 2007, and then northward summer, the atmosphere became noticeably more active. Cloud features appeared, storms developed. The banded structure of atmospheric circulation that planetary scientists expected but could not see in 1986 began to emerge. The planet that looked dead in one photograph taken during one brief flyby is, in fact, seasonally alive. It was simply the wrong season when Voyager arrived. The tilt also produces something visually extraordinary when Uranus is near its solstice, the moment when one pole is pointed most directly at the sun. From Earth, looking at Uranus at solstice is like looking at a target. The planet appears as a disk, with its rings forming a series of concentric circles around it. The bullseye geometry that complicated Voyager 2's flyby trajectory. The rings are edge-on to the viewer at equinox, nearly invisible. At solstice, they are face-on, fully visible. A set of dark, faint rings encircling the pale blue disk in perfect symmetry. The rings themselves deserve a brief mention here. Unlike Saturn's rings, wide, bright, and spectacular, Uranus's rings are narrow, dark, and difficult to see. They were discovered in 1977, just months before Voyager launched, when Uranus passed in front of a background star and astronomers watching the star's light noticed it dimmed briefly before and after Uranus occluded it, a signature of rings blocking the starlight on both sides. There are 13 known rings in total. The outermost ring, called Epsilon, is the brightest and widest, still only a few kilometers wide in most places. The rings are made of dark material, possibly carbon-rich, and are kept narrow and sharp by the gravitational influence of small shepherd moons, Cordelia and Ophelia, that herd the ring particles back into line whenever they start to spread out. Without those two tiny moons on either side of the Epsilon ring, the whole structure would gradually disperse. One planet, rolling on its side. 42-year seasons of continuous light and darkness. A set of narrow, dark rings kept in place by two shepherd moons, named after characters in Hamlet and Othello. A cartwheeling magnetic field generated by superionic water in its interior. 29 literary moons, one of them just discovered and still waiting for its Shakespearean name. A cooling atmosphere whose cause nobody understands. An interior that might be rock or ice or something in between. The mystery of why it has no internal heat. And at the center of all of it, the original question still unanswered. What hit it? One thing. Two things. Or a moon that spent millions of years quietly, impatiently, pulling the whole planet sideways before disappearing into it forever. Every answer about Uranus leads to another question. That is not a failure of science. That is what genuine mystery looks like. And genuine mystery is why, when the people who study the solar system for a living sat down and decided where to go next, they looked at this tilted, strange, poorly understood world at the edge of the solar system and said, "There, that one. We need to go back. Everything we have covered so far, the discovery, the flyby, the missing heat, the bizarre tilt, the 29 literary moons, has been about Uranus as a member of our solar system. A planet orbiting our sun, one of 8, a neighbor in the cosmic sense. But there is a bigger reason why planetary scientists are so urgently pushing for a return mission to Uranus. A reason that has nothing to do with our solar system and everything to do with the rest of the galaxy. Exoplanet surveys have been running for 3 decades now. Since the first confirmed detection of a planet orbiting another star in 1992. Astronomers have catalogued thousands of worlds beyond our solar system. And one pattern has emerged from that catalogue more clearly than almost any other. The most common type of planet in the Milky Way is not a gas giant like Jupiter. It is not a rocky world like Earth. It is something in between. A planet roughly the size and mass of Uranus or Neptune. An ice giant. And we have barely studied ours. This matters enormously. When astronomers discover an exoplanet orbiting a distant star, they can measure its size, estimate its mass, and sometimes analyze the composition of its atmosphere from the light that filters through it during a transit. But to truly understand what that planet is, what its interior structure looks like, how its atmosphere circulates, what drives its magnetic field, whether it could support moons with liquid water, oceans, they need a reference, a known example, a planet they have studied in detail that they can compare the exoplanet against. For gas giants, Jupiter and Saturn serve as those reference points. For rocky worlds, Earth and Mars serve that purpose. But for ice giants, the most common type of planet in the galaxy, the reference points barely exist. We have Uranus and Neptune, both of them visited once, briefly, nearly 40 years ago. And between those two flyby snapshots and the thousands of ice giant exoplanets astronomers are trying to interpret, there is an enormous scientific gap. Every time JWST points at a distant star and detects a Neptune-sized world in its data, the scientists trying to understand that world are working without a proper reference. They are trying to describe a type of planet whose 2 nearest examples we have never properly characterized. It is as if we were trying to understand terrestrial planets across the galaxy, having visited Earth only once for 6 hours during a hurricane. That is the context in which the push for a Uranus orbiter mission must be understood. This is not a mission about Uranus in isolation. It is a mission about understanding a class of planet that makes up a significant fraction of all planetary systems in the Milky Way. Getting Uranus right means getting ice giants right. And getting ice giants right means getting planetary science right for an enormous proportion of the worlds that exist in our galaxy. The mission that planetary scientists want to send is called the Uranus Orbiter and Probe. It was ranked the top priority for the next NASA flagship planetary science mission in the 2023 Planetary Science Decadal Survey. The 10-year roadmap that the scientific community produces to guide NASA's priorities. Flagship missions are the biggest, most expensive, most scientifically ambitious missions NASA undertakes. Cassini was a flagship. Curiosity and Perseverance on Mars are flagships. The Europa Clipper, currently traveling to Jupiter, is a flagship. A Uranus flagship would be in that league, a multi-billion-dollar, multi-decade commitment to finally understand the seventh planet. The mission design, as currently conceived, would involve two components. The first is an orbiter, a spacecraft that would enter orbit around Uranus and spend multiple years studying the planet, its rings and its moons from close range. It would measure the gravitational field with enough precision to finally constrain the interior structure and determine whether Uranus is ice-rich or rock-rich or something else entirely. It would study the magnetic field across a full range of solar wind conditions, not just the 4% bad day that Voyager 2 encountered, but the full 96% of normal behavior that has never been directly observed. It would image the major moons in detail for the first time, looking for signs of geological activity, searching for the electromagnetic signatures of subsurface oceans on Ariel and Titania and Oberon. It would watch the atmosphere change with the seasons, tracking the circulation patterns and storm systems that Voyager 2 never saw. The second component is an atmospheric probe, a small spacecraft that would separate from the orbiter and plunge directly into Uranus's atmosphere, transmitting data as it descends until the pressure and heat destroy it. As it falls, it would directly sample the chemical composition of the atmosphere layer by layer, measuring the abundances of hydrogen, helium, methane, ammonia, water vapor, and heavier molecules that no instrument has ever directly sampled before. It would measure temperatures and pressures at each depth. It would look for lightning. It would characterize the cloud layers that we currently only know must exist from theoretical models. The probe would probably survive for an hour or two before the atmosphere crushed it. In that hour, it would return more direct data about Uranus's atmosphere than everything combined from Voyager 2, Hubble, and JWST. The earliest realistic launch window for this mission, given the current state of NASA's budget and planning timelines, is somewhere in the early 2030s. If launched in 2031 or 2032, using Jupiter as a gravitational assist, the spacecraft would arrive at Uranus sometime around 2044 or 2045. That is 20 years away. The scientists who wrote the decadal survey recommending this mission are planning for a result they will not live to see fully realized. Some of the graduate students who will actually operate the spacecraft when it arrives at Uranus are in primary school right now. This is one of the things about planetary science that is easy to overlook. It operates on timescales that have no parallel in almost any other human endeavor. A scientist who dedicates their career to Uranus today might spend 30 years building toward a mission that will not return its primary science until after they retire. The results of decisions being made right now in budget meetings and mission planning committees will not be known until the 2040s. The patience required, the willingness to work toward results you may never personally witness, is one of the most extraordinary aspects of this field. And yet people do it. They have always done it. The engineers at JPL, who built Voyager 2 in the 1970s, knew the Uranus flyby would not happen until 1986. They built it anyway, because they understood that the value of the knowledge that would come back was worth the wait. The scientists who will spend the 2030s and 2040s building and launching and guiding a Uranus orbiter understand the same thing. The universe does not operate on human timescales. The answers we are seeking about Uranus were baked into the planet 4.5 billion years ago. They will still be there in 2044. We just have to be patient enough to go and find them. While we wait for that mission, Uranus continues to give up its secrets slowly and imperfectly through the instruments we have. JWST will continue observing it. Hubble will continue tracking its seasonal changes. Ground-based telescopes equipped with adaptive optics will continue hunting for new moons, monitoring the rings, watching the atmosphere evolve through its extraordinary 42-year seasonal cycle, and somewhere in an archive of data that was collected in 6 rushed hours in January 1986, there may still be discoveries waiting, patterns nobody has noticed yet, measurements that have been reinterpreted in light of new knowledge, anomalies that suddenly make sense when viewed through a different theoretical framework. Voyager 2's data from Uranus has been analyzed continuously for nearly 40 years, and it is still yielding new science. It yielded new science just weeks ago. That is what happens when you have only one dataset from only one visit to a complex, mysterious world. Every analysis, every reinterpretation, every new technique applied to old data is potentially a discovery. The 7,000 photographs that Voyager 2 returned from Uranus in 1986 are still being studied. The measurements its magnetometer made in those 5.5 hours are still being modeled. The planet has been talking to us continuously since that flyby. We have simply been getting better, slowly, at learning how to listen. There is one final thing worth saying about Uranus, and it is perhaps the most important point in this entire journey. Uranus is strange, deeply, persistently, surprisingly strange, or strange in ways that were not fully appreciated until recently. Strange in ways that are still being discovered. Strange in ways that challenge the models, rewrite the textbooks, and force planetary scientists to go back and rethink assumptions they had been making for decades. And That strangeness is not a problem. It is a gift. The history of science is a history of the strange becoming understood. The planets themselves were once strange, wandering lights that moved against the fixed stars, inexplicable to everyone who watched them until Kepler and Newton provided the mathematics that made them simple. The interior of the Earth was once a mystery, an unreachable void about which people could only speculate until seismology gave us the tools to map it with sound waves. The structure of the atom was profoundly strange when physicists first began to probe it. And out of that strangeness came quantum mechanics, which is the foundation of every piece of technology you are using right now. Strangeness is how the universe signals that there is something important to understand, something that, once understood, will change everything. Uranus is strange. Its tilt is strange. Its missing heat is strange. Its magnetic field is strange. Its cooling atmosphere is strange. Its interior, which might be rock or ice or something in between that no one has properly named yet, is strange. And somewhere in all of that strangeness, packed into a pale blue-green disk, rolling quietly through the outer solar system on its 84-year orbit, are answers to questions about how planets form, how they evolve, how common liquid water is in the outer solar system, how ice giant exoplanets work and what they are made of, and whether any of them might be hospitable to life. Questions whose answers matter not just for understanding Uranus, but for understanding the galaxy it lives in. We have not gone back yet, but we are going back. It will take 20 years. The spacecraft is not built. The budget has not been fully approved. The scientists who will operate it have not all finished their educations. And Uranus will be there when we arrive, rolling on its side, its literary moons circling in their Shakespearean parade, its magnetic field cartwheeling through space, its secrets intact, patient as only a 4-billion-year-old planet can be patient, waiting for us to finally show up and ask the right questions.